Hello everyone. In this video, I'm going to be talking to you about assessing the accuracy of y hat. Y hat here, which we get in this equation right here, and this is as a result of using our sample observations to obtain here an estimate of the mean level of y for a given x. The mean level, of course, which is one of the two components needed in the regression equation, the regression model equation that we have right here. So let's not forget that y is made up of two different parts. The mean level, or the explained part of y, so y being explained in terms of x, and then the unexplained or the random part of y, which is also called the error term component, which is everything else that is found in y that cannot be explained by x, or the regression line, if you want. So we get here our y hat, once again, through the method of least squares, in order to come up here with estimates for beta naught and beta 1. And so, yes, so that comes from our regression, from our sample, our randomly selected sample of n observations. And so the y hat value that we get over here will change for each different x value that we plug in this equation, right? In this fitted regression line equation. So let's go back to our example of 10 randomly selected observations of restaurants here. And what we see is that we get here these 10 different y annual revenues for 10 given x values of population size. Okay, and so as a result of using this sample of 10 observations, we get the following fitted regression line equation right here through the method of least squares. Now, understand that these values I get here for beta, well, for B naught, this is B naught, and for B1 right here, well, this is highly dependent on my sample observations that I'm getting right here. If I had obtained different y values for these x values right here, then my fitted regression line would be different. Not very different, I would hope, but different to some extent. Okay, so just understand that it is possible to get different y hat values for a given x, for one specific x value, when I know that there are n possible, when I know that there are many other possible yi values out there, right? If I know that there are different other observations y out there for a given x, well, of course, this will overall give me a different fitted regression line. Okay, so now I move on to illustrate an example here. So to talk more about y hat. So what is really y hat? So if a restaurant manager, say, is interested in opening a restaurant in an area of a population size X, say here equal to 47,300 residents, then the restaurant manager could use this equation right here in order to determine what would be the average annual revenue that any restaurant in such an area of 47.3 thousand residents earns on a yearly basis. So the y hat value that I would be getting here by plugging in my 47.3 would in fact give me an average or mean yearly revenue that is expected of restaurants built in areas of such a population size. So that is an important information that a manager can use, of course, but it does not necessarily guarantee that the manager will earn such an income at the end of the year, right? The manager could possibly earn more or less or close to the average value, right? So this only gives you average values by plugging in for different X values over here. So now that you understand that, you must also understand it once again, I've mentioned it before, but I'll say it again, and that is that if I had based my fitted regression line right here on a different sample of Y values, then I'd be getting here a different B naught and B1, and so that would give me a different average Y hat value right here for a given X. So that being said, I know that there are many Y hat values out there for a given X value, for a given population size. And so, with that in mind, I would like to assess here the accuracy of the Y hat values. In order to do that, I'm going to need my 4 model assumptions that I had uh, established from before about the error terms, the epsilon of I, or the residuals. And so very quickly, these are the 4 model assumptions that are summarized in this statement right here. Okay, so if that holds, if these 4 model assumptions hold, then the next thing is that now I can make some assumptions about my Y hat. And that is that all the possible Y hats that are out there for a given X value equal to, say, X of A, will be normally distributed. It will be normally distributed about the true Y hat value, the true population Y hat value. What is that true population Y hat value? Well, that true population Y hat value is right here, mu of Y for a given X. So imagine I've got a bunch of Y hat values for a specific X equal to, say, X of A, and that will give me a specific mu of Y value over here. So my Y hat values will be spread out, will be distributed around this mu of Y. And they will be distributed around this mu of Y in a normal fashion, in a normal way. Okay, and further, what I can say is that all these different mu of Y hats for that same X equal to X of A will have a standard deviation, an estimated standard deviation, which I get here from my sample, and that will be called the standard error of Y hat. The standard error of Y hat is this right here. It follows this form. So S of Y hat is equal to here the product of the standard error of the residuals. Remember, S is the standard error of the residuals, which in fact is equal to the square root of the mean squared errors. Okay. Times over here this little part, which the square root of this part here is what you call also the square root of the distance value. So I'm going to talk about the distance value in just a little bit here. So basically, if I'm able to get the standard error of the Y hat, then that means I can also build an interval, more specifically, a confidence interval for the true population mean value of Y at a given X value. I can build that confidence interval around my point estimate Y hat that I am getting from my sample for a given X equal X of A. Okay. So this confidence interval now, if you remember what you need to build a confidence interval number one is your point estimate. My point estimate here is my y hat that I get from my sample for a given x value. X equals x of a over here. So in the example I was looking at before, my x here was specifically equal to 47.3. Okay, and as a result, I get a specific here point estimate y hat, which we said was equal to 920.98, right, in thousands. But of course, if I change my x of a to be another value, well, then I will get here a different point estimate y hat. Okay, so we focus on one x value at a time to get point estimates y hat over here. That is the first part of the confidence interval. The next part that I need is that margin of error. That margin of error is the critical value. So here I'm using t-points to be my critical values over here. And the t-points are based on my confidence level that I specify when I'm building a confidence interval. So if I'm building a 95% confidence interval, then I'm going to be looking at t-points for 0.05 over 2, which gives me 0.025. So I'm looking at t-points for 0.025 areas in the tails, and degrees of freedom here will be equal to n minus 2. N minus 2 because my y hat here is based on two estimated parameters. Over here, my beta naught is estimated and my beta 1 is estimated. Hence, I have here 2 degrees of freedom. Sorry, I have n minus 2, so I lose 2 degrees of freedom here in my t point. Yes. And so that is the first part of the margin of error that we need to input in here. The second part, of course, is the standard error of the point estimate. The standard error of the point estimate, S of y hat, which we define right here. Okay, and so if I have all these elements, then I can generate 1 minus alpha times 100% confidence interval for mu of y, of course, for a given x value. Okay. Further to that, I can also here obtain a point prediction. Okay, a point prediction y over here. So let me talk to you a little bit more about that. Okay, so say now the restaurant manager wants to know, okay, say the restaurant manager that I was talking to you about originally wants to know more information than just the mean value of annual income of a restaurant for restaurants located in an area where population size is of, say, 47.3 thousand residents. Say now the restaurant manager wants to get here a range of values for possible individual annual incomes that can be obtained of restaurants located in this area of population size of, say, 47.3 thousand residents. Okay, well, in that case here, we need to build here a prediction interval. We are no longer looking at a confidence interval around y hat, but rather a prediction interval which will be based on the mean value y hat for a given x value. Okay, so we say here that we need to, first of all, examine the prediction errors, y minus y hat, all the possible prediction errors that are out there relative to the mean value y hat for a given x value. Okay, and so we say that these prediction errors if the four model assumptions on the error terms that we saw before, on the residuals that we saw before. So let me just show you very quickly what these are once again. Yes, so these error terms, if they are distributed in the following way, then it follows that the prediction errors that we get right here, these are the all the individual y values that we will get around our our fitted regression line value y hat for a given x value. Well, these prediction errors will be normally distributed as well, and they will have a standard deviation estimated from the sample, which we call the standard error of the y minus y hat. And this will follow this form right here. So we say that the standard error of the y minus the y hat is equal to, so this S, which is the standard error of the residuals, let's not forget that is equal to the square root of the mean squared error, okay, times this over here, this component right here. So notice here, this is very similar to the previous part that we saw in the formula for the standard error of the y hats, right? We had this part right here in the square root, okay? However, here we do have an added component in the square root, and that is this 1, where this extra 1 really is purposely there to account for the fact that we are now adding a level of uncertainty when working with the standard error for prediction errors. When we work with the standard error for prediction errors, in fact, we are adding another layer of uncertainty in predicting an individual value of y. So now we are interested in predicting what will be the true y value. We are not interested in a mean value of y, but rather an individual value of y for a given x. So there is another layer of uncertainty that is added in there. Hence, we have this 1 added in the square root. Okay? And so further, we can build a prediction interval now. So you have here a 1 minus alpha times 100% prediction interval for y, for the true y value for a given x value. And that prediction interval is expressed as the following here. So it is built around our point prediction. So now we are talking about point prediction. This point prediction is y hat. That is our fitted regression line value of y for a given x. Okay, so it is built around there, and on it we put a margin of error, plus or minus this margin of error. The margin of error here is made up of this critical point t, the same critical point that we used to build the confidence interval for mu of y, right? So it is that same critical point, but this time we will be multiplying that critical point in the margin of error by a standard error for over here, S of y minus y hat. So a standard error for the, let me just enlarge it here, for the prediction error, right here. Okay, so in other words, we multiply by this over here. And so this will give us the prediction interval for an individual value of y for a given x. So if we want to look at this in a picture, this is what is happening actually. Okay, what's happening is here we have our estimated regression line. This is coming from our sample of n observations. And we can see how y hat here will take on different values for different values of x, right? These are the x values, these are the y values, and we see how the fitted y hat values here take on different values for different x values. And these are, of course, the mean value of y, right? They're estimated mean values of y. And so around this mean value of y for different x values, we build first a confidence interval. So these are the yellow lines that we see around the blue line. These are the, so this is the confidence interval for different x values, right? So we see that we have different y hat values that can potentially be um, taken on for different x values. That is when we add our margin of error using over here the standard error for y hat. So let's just go back to that formula. The standard error for y hat is this over here. Okay, and so that is what gives us this confidence interval, which you see right here. Okay. Notice here how the confidence interval changes in width. Um, it is more narrow when we are more in the center of the x values. So in other words, when we are closer to the average value of the x values over here, so in other words x bar, the closer our x value is for a y hat. Remember here, for each x value, there is a different y hat value. And so the confidence interval is different around that y hat. So in the example I gave you, I said, let x here be equal to 47.3. If 47.3 happens to be close to my x bar, to my average x value over here in the center, then my confidence interval will be tighter. It'll be smaller. It'll be closer to y hat, right? And as I use x values that go further and further away from the center of all the x values, that they go further away from x bar, the mean value of x, then notice how my confidence interval is getting wider. And that is because, in fact, my margin of error is getting longer, right? Because now what happens is, let's go back to that formula very quickly for the standard error of y hat. Let's just see over here. So what's happening in this component of the square root? This is what we call the distance value over here. This distance value over here, what's happening is that as x of a is going further from the center of all the x values, hence it is deviating more from x bar, well, this value in the numerator is getting larger. And so if it's getting larger, this means overall my distance value in the square root is getting bigger. If the distance value in the square root is getting bigger, that means overall my standard error of y hat over here will get larger. Hence my confidence interval, so this is my confidence interval right here, will get bigger as well, right? I'll get a longer confidence interval. Let's just go back to our graph. Here we are. Okay, so that explains why the confidence interval is getting wider as we move away from x bar. Now the prediction interval, that is the pair of green lines that we see over here. The prediction interval, you can see by default, is already wider than the confidence interval for y hat. For y. So the prediction interval here is intended to predict where an individual value of y will fall for a given x, right? And we can see here how the prediction interval is based on the y hats for different values of x, but the margin of error that is built around the y hat is longer. the margin of error is longer, and that is reflected by the fact that here in the standard error of the prediction error, y minus y hat, we have here in the square root formula here, we've got the distance value, which we identified before, plus this 1, the 1 being that added uncertainty as to where an individual y will fall about the y hat for a given x value. Okay, so that is what you need to think about. So prediction intervals are always wider than your confidence intervals about your point estimate y hat. Okay, that is just a general rule over here. And here I explain just a little bit more on distance value. So these are the different ways that you can represent the distance value. It's a new concept over here. So we say that the distance value is in fact equal to this part here, which we saw in the square root for the standard error of the y hat, right? And you can see how the distance value will become larger as the deviation between a given point with an x of a value that is further away from your mean value of x. So as this gets larger, your distance value will get larger as well. And so then, yes, so then that means that over here we can express our confidence interval from mu of y to take on this form as well. Okay, so the form that we saw before for a confidence interval for mu of y for a given x, it was, let's go back very quickly, was expressed in this format right here. Well, this can be also expressed as, in terms of distance value, it can be expressed as the following right here. Here we are. So confidence interval from mu of y for a given x equal to x of a is equal to my point estimate here, mu of y, y hat, that's coming from my sample, plus or minus here this margin of error. So this margin of error here is now the standard error of the residuals here times the square root of the distance value being equal to this right here, and times, of course, my critical point. For the prediction interval for y for a given x equal to x of a, then I can see how it is expressed in this form right here. So again, I'm using my point prediction now. So y hat now serves as a point prediction. It still has the same value as the y hat in the confidence interval, but now I'm going to use it as a point prediction. Okay, so in other words, it's a point prediction now because I'm building a prediction interval around it. So notice here how my standard error of the point estimate here is now expressed in the following terms. It's the s times the square root of 1 plus the distance value. Okay, and so here I just want to yes, this is an important point to note as well. The distance value then can also be expressed in this form. It is equal to the standard error of the y hat. Okay, so that is this right here. That is what the standard error of y hat is, divided by s, and square all that. So that is how you can express the distance value. So when you go from here to here, that is how you get your distance value. Now in an Excel regression output, this is the type of information that you get. So you get here your standard error, that's your S, that's your actual S value right here. But in order to get the distance value from an Excel output, you'll have to compute S of y hat for a given x, right? So Excel does not actually give you the distance value. at least to the last that I checked, I don't think it can give you the distance value, but maybe more recent versions of Excel might be able to provide that information. Okay. So you need to compute over here S of y hat for a given x value. And that can be done. It just requires a little bit of arithmetic over here. You can get over here the distance value by computing this right here. Okay, and once you have your distance value, then you can take the square root of it and multiply it by the standard error over here that you get from Excel, right? That's your square root of MSE once again, and hence you can get here your confidence interval. Now, on the other hand, if you are using Minitab has this advantage of providing more information. You can actually get here your prediction interval directly from Minitab. What you need to do here is identify what your x value will be in order to obtain your confidence interval and your prediction interval. So all you need to do is enter your x value, right? Because that's what you need in the first place. So we were working with the example of 47.3 being the population size for x. So if that is my population size, what I get as a fitted value of y, that's my y hat, is in fact 920.98, if you want, 98. That's exactly what we were saying before. That's my estimated annual income, right? And so from there, what I get here is my fitted value, my standard error fitted value. Let me just check over here. This this S of E fit statistic that I'm getting over here is in fact, this is my standard error of y hat. This is my standard error of y hat for a given x value here of x equal 47.3. So this is the actual S of y hat. Okay? So this is not information that you're able to get in Excel, but you can get it in Minitab. And if I have my standard error of y hat, then I can go ahead and build my my confidence interval for mu of y at x equals 47.3, and here it is. So I see how my confidence interval ranges from 874 about to 967 approximately, right? Versus here my prediction interval. So my prediction interval can also be obtained over here by using the standard error of y hat, okay? And if I have my standard error of y hat and my standard error of the residuals over here, well, let's not forget that the distance value is equal to S of y hat over S all squared, right? So I do have all that information in Minitab, and so I can get my distance value. If I can get my distance value, then all I need to do is, build my prediction interval around y hat by adding and subtracting over here this margin of error. Well, Minitab does it for you. You don't need to do it, but you can check manually just to make sure that it does make sense. And here you'll see that the prediction interval is, in fact, wider than the confidence interval. So here I get 771 to 1070.75, right? So you can see how the prediction interval is wider than the confidence interval. And so that concludes our simple linear regression analysis. So I hope you've enjoyed this video. Thank you.